Let's begin with this one. I gave you a little picture there. Evaluate the surface integral of a vector field over the surface given. That surface for number 6 is the graph z equals negative x minus y minus 1 over the rectangle 0, 1, 0, 1. That's x and y coordinates, and it's down there. So the actual surface is this parallelogram over this rectangular region, right? So it said surface integral over a surface, and sometimes they don't specify in the book integral over a curve. Then you assume it's line integral, right? Over a curve, you don't do the surface integral over a curve. Curve means line integral, and here they specified everything, I realize. So we're doing surface integral, right, over vector field. So that's the surface, and here is how the vectors is passing through. It's all going downwards. So that thing that we are calculating represent number of things as particle that's passing through this plate over there. All right, it was a homework problem. So let's begin our first exercise to be this one, and see if you can calculate this one and check your understanding and answers. How was it? Is that okay? So first, you always have to begin with the parameterization of the surface. That's how you approach. If it is a direct calculation, so it's a graph of a function. Z is isolated like this, so we use this modular parameterization. X and Y are just free variable, and Z is whatever you get out of this formula in terms of S and T. So RSRT, I memorized the formula. The answer is negative Fs, the formula, negative Ft, and 1. So if you do the partial derivative and change the sign, you get 1, 1, 1. Constant, right? Because there was a plate, that makes sense. This also can be read from plane equation, x plus y plus z plus 1 equals 0. That's the same thing. So that's how you read the normal vector, right? the coefficient of x and y and z. But that's also the same thing we got out of parameterization. So if you dot, this is the parameterization free notation. That's how we write. And this is actually how we calculate. And I don't mind if you go from here to that directly using that formula I gave you before. For some reason I keep doing that. I think I still feel comfortable within this way of looking at the problem. So that was one of the homework problem. Direct calculation is what I say, right? Okay. So when the line integral is given and they ask you to direct calculation, that means you don't use trick of fundamental theorem of line integral or Green's theorem. You do honest calculation. You take the parameterization, plug it into the formula, do the dy, dx, dt, and actually calculate the dt integral, right? That's the direct calculation. But we have two more methods for line integrals, right? Using fundamental theorem or Green's theorem. And here we're looking at the surface integral, and Stokes' theorem sometimes, gives you one different method, but this is just direct calculation. Any question about this problem? All right, let's review.